The idea that the neutron is electrically neutral yet crucial to the stability of all matter sounds simple at first, almost obvious to anyone who has encountered basic atomic theory. But when explored deeply, this single statement opens a vast landscape of physics, philosophy, and cosmic history. It describes how the universe learned to hold itself together. It explains why matter did not dissolve into chaos moments after the Big Bang, and why atoms could grow complex enough to form stars, planets, and eventually life. The neutron's lack of electric charge is not a minor detail. It is the very reason stability exists at all. To understand this, one must begin with the early picture of the atom. Atoms were once imagined as tiny solar systems, with electrons orbiting a dense nucleus. That nucleus was known to contain positively charged protons. This immediately raised a terrifying question for early physicists. Like charges repel. If protons are all positively charged and packed into an incredibly small space, the nucleus should violently explode apart. According to the laws of electromagnetism, there was no reason for atomic nuclei to exist beyond a fleeting moment. And yet, matter was clearly stable. Rocks did not disintegrate. Stars burned steadily for billions of years. Something invisible was acting against electrical repulsion. The neutron entered this mystery as a silent mediator. With nearly the same mass as a proton but no electric charge, it could occupy the nucleus without increasing electrical repulsion. This single property transformed the nucleus from an impossible structure into a stable one. Neutrons allowed protons to sit close together, while the strong nuclear force, a force far more powerful than electromagnetism at very short distances, could bind them into a tight, stable core. Without the neutron's neutrality, this balance would collapse. If neutrons carried positive charge, they would add to the repulsion. If they carried negative charge, they would distort atomic structure in other destructive ways. Their neutrality is not accidental. It is perfectly tuned to allow matter to exist. The stability provided by neutrons is not uniform or simple. Different atoms require different numbers of neutrons to remain stable. Light elements like hydrogen can exist without neutrons, but they are fragile and limited. As atoms grow heavier, neutrons become essential. Carbon, oxygen, nitrogen, iron, and every element that builds living organisms depends on neutrons to counteract increasing proton repulsion. As the number of protons increases, so must the number of neutrons. This delicate ratio defines whether an atom is stable or radioactive. Too few neutrons and the nucleus falls apart. Too many and it becomes unstable in another way. Stability is achieved only in a narrow window governed by the neutron. This balance reveals something profound about the universe. Stability is not guaranteed by strength alone, but by neutrality and balance. The neutron does not dominate by force or charge. It stabilizes by existing without interference, allowing stronger forces to do their work without disruption. This principle echoes throughout nature, from atomic structures to ecosystems and even social systems. The neutron's role suggests that neutrality can be a form of power more fundamental than aggression. The importance of neutron-driven stability becomes even clearer when considering the early universe. Shortly after the Big Bang, the universe was a hot, dense soup of particles. Protons and neutrons formed within minutes, but only briefly existed in equilibrium. As the universe cooled, neutrons began to decay into protons. Only those neutrons that became bound inside atomic nuclei survived. This survival allowed the formation of helium and small amounts of other light elements. These early nuclei became the seeds of all future matter. Without neutrons surviving long enough to form stable nuclei, the universe would contain almost nothing but hydrogen. No complex chemistry, no stars like our Sun, no planets, and no life. The neutron's neutrality also allows it to interact in ways charged particles cannot. Protons and electrons are strongly influenced by electromagnetic fields. They are deflected, repelled, or attracted easily. Neutrons, having no charge, pass through matter with relative ease. This property allows them to penetrate deep into atomic nuclei and influence reactions from within. It is why neutrons are so effective in triggering nuclear fission and sustaining nuclear chain reactions. It is also why neutrons play a crucial role in stellar processes, slipping into nuclei and enabling the creation of heavier elements inside stars. At a deeper level, the neutron challenges our understanding of what stability means. Inside a nucleus, a neutron can remain stable for billions of years. Outside the nucleus, it decays in minutes. This contrast shows that stability is contextual. The neutron is not inherently stable or unstable. Its fate depends on relationships and structure. Bound to protons, it becomes part of a lasting system. Alone, it transforms. This teaches a powerful lesson about matter itself. Particles are not isolated entities with fixed destinies. Their behavior emerges from interactions. The neutron also reshaped scientific thinking by revealing that electric charge is not the only organizing principle of matter. Before its discovery, charge seemed central. Positive and negative defined attraction and repulsion. The neutron introduced a third category: massive, influential, and neutral. It forced physicists to recognize the strong nuclear force as a separate, dominant interaction at small scales. This realization opened the door to modern particle physics and quantum field theory. The neutron was not just a particle. It was evidence that reality operated on rules deeper than classical intuition. As elements grow heavier, neutron stability becomes even more critical. In heavy nuclei, the number of neutrons must exceed the number of protons significantly to maintain stability. These neutrons act as spacers and force carriers, allowing the strong force to counterbalance increasing electrical repulsion. When this balance fails, radioactive decay occurs. Atoms emit particles or energy to move towards stability. In this sense, radioactivity itself is a story of neutron imbalance. The neutron determines whether an atom will endure for billions of years or decay in fractions of a second. This has enormous consequences for the natural world. The heat inside Earth, generated partly by radioactive decay, depends on unstable nuclei with imperfect neutron-proton ratios. The age of rocks can be measured because neutrons influence decay rates. Medical imaging and cancer treatments rely on radioactive isotopes whose behavior is governed by neutron stability. Even the ticking of atomic clocks, the most precise timekeeping devices ever created, depends indirectly on atomic structures stabilized by neutrons. In stars, the neutron's stabilizing role extends beyond individual atoms. During stellar fusion, nuclei are forced together at extreme temperatures and pressures. Protons alone cannot easily combine because of their repulsion. Neutrons allow fusion pathways that would otherwise be impossible. In massive stars and explosive events like supernova, rapid neutron capture processes create many of the heavy elements found in the universe. Gold, silver, uranium, and dozens of other elements owe their existence to environments rich in neutrons. These elements later become part of planets, technologies, and living organisms. The neutron, neutral and unseen, becomes the architect of cosmic diversity. Even the existence of stable matter over cosmic timescales depends on neutron behavior. If neutrons decayed faster, or if their mass differed slightly from that of protons, the balance of the universe would change dramatically. Small variations in neutron properties would prevent the formation of complex nuclei. Physicists often point to this as an example of fine-tuning in the universe. The neutron's neutrality and mass are not random features. They are precisely what allow matter to persist. There is also a philosophical dimension to the neutron's role in stability. It contradicts the intuitive idea that influence requires visibility or interaction through obvious forces. The neutron exerts its influence precisely because it does not participate in electromagnetic conflict. It sits quietly, enabling stronger forces to act without chaos. This suggests that the deepest stability in nature arises not from dominance, but from balance and restraint. From the smallest atomic nucleus to the largest structures in the universe, the neutron's neutrality underpins existence. Galaxies form from stars, stars form from atoms, atoms form from nuclei, nuclei hold together because neutrons make it possible. Remove the neutron, and the entire hierarchy collapses. Matter becomes fragile, simple, and short-lived. Complexity vanishes. The neutron does not announce its importance through charge or light. It leaves no visible trail. Yet every solid object, every breath of air, every living cell is a testament to its stabilizing presence. It is the quiet reason matter does not tear itself apart. In that sense, the neutron is not merely a particle among others. It is the condition that allows matter to exist at all. This is why the statement that the neutron is electrically neutral yet crucial to the stability of all matter is not just a scientific fact, but a summary of the universe's success. It captures how something seemingly passive and invisible can be absolutely essential. The neutron shows that neutrality can be power, that silence can be structure, and that the foundations of reality are often built from what appears, at first glance, to do nothing at all. The idea that neutrons hold atomic nuclei together through the strong nuclear force reaches far deeper than the common description of them as simple neutral particles. It is a story about how nature solved one of its most fundamental problems: how to allow matter to exist in a stable, long, lasting form without collapsing or exploding. At the heart of every atom lies a constant struggle between forces that want to tear matter apart and forces that want to bind it together. The neutron stands at the center of this struggle, not as the strongest participant, but as the one that makes strength usable. Inside an atomic nucleus, protons are packed into a region unimaginably small. Each proton carries a positive electric charge, and according to electromagnetism, like charges repel. This repulsion is not weak or theoretical. It is powerful and unavoidable. If electromagnetic force were the only interaction at work, no nucleus beyond a single proton could survive. The universe would be limited to hydrogen, and even that would be precarious. The existence of heavier elements proves that another force must overpower this repulsion at extremely short distances. That force is the strong nuclear force, the most powerful force known in nature. It operates only over distances comparable to the size of a nucleus, but within that range, it overwhelms all others. The strong force binds protons and neutrons together, forming a tightly bound nuclear core. However, the strong force alone is not enough to explain stability. Its behavior is subtle, and this is where the neutron becomes essential. the strong nuclear force does not act equally in all situations. It is attractive at very short distances, but becomes repulsive if particles are forced too close together. This delicate balance prevents nuclei from collapsing into a single point. Neutrons play a crucial role in maintaining the correct spacing and structure within the nucleus. Because they carry no electric charge, neutrons can approach protons without adding electromagnetic repulsion. This allows the strong force to act efficiently, binding particles together without being undermined by electric forces. The neutron effectively acts as a buffer between protons. By sitting among them, it increases the reach of the strong force without increasing electrical instability. This is especially important in heavier nuclei, where the number of protons grows large and electromagnetic repulsion becomes intense. Without enough neutrons, the nucleus becomes unstable and falls apart through radioactive decay. With too many neutrons, it becomes unstable in a different way. Stability emerges only when neutrons and protons are balanced in a precise ratio governed by the strong force. This balancing act is not static. It reflects the dynamic nature of nuclear matter. Neutrons and protons are constantly interacting through the exchange of particles called gluons and mesons, which transmit the strong force at the fundamental level. These interactions create an energy landscape within the nucleus that determines whether it remains intact or decays. Neutrons contribute significantly to this landscape by participating fully in the strong interaction while remaining invisible to electromagnetic forces. The importance of neutrons becomes clearer when considering isotopes. Isotopes are versions of the same element that differ only in the number of neutrons they contain. Some isotopes are stable, while others are radioactive. The difference often comes down to how well neutrons can mediate the strong force within the nucleus. A stable isotope has just the right number of neutrons to maximize binding energy. An unstable one has too much or too little, causing internal stress that leads to decay. In this sense, radioactive decay is a failure of neutron-mediated stability. The strong force itself is blind to electric charge. It does not care whether a particle is positive, negative, or neutral. It only cares about proximity and internal quantum properties. Neutrons are therefore ideal participants in strong force interactions. They contribute mass and binding potential without interfering with electromagnetic balance. Protons, by contrast, always bring repulsion along with them. Neutrons allow nuclei to grow larger and more complex than protons alone ever could. This role becomes dramatic in the formation of elements inside stars. In stellar cores, temperatures and pressures are so extreme that nuclei can overcome their electromagnetic repulsion and fuse together. Neutrons are often produced and captured during these processes. Their presence allows nuclei to absorb additional mass without increasing charge, making it easier for the strong force to bind the nucleus. Over time, this leads to the creation of heavier elements. Every carbon atom in your body and every iron atom in your blood exists because neutrons enabled the strong force to build stable nuclei in ancient stars. The story becomes even more intense in explosive cosmic events. During supernova and neutron star mergers, vast numbers of neutrons are released in a short time. These neutrons are rapidly captured by atomic nuclei in a process that creates many of the heaviest elements in the universe. In these moments, the strong force, guided by neutrons, reshapes matter on a cosmic scale. The gold in jewelry, the uranium in reactors, and the iodine in medicine are all products of neutron. rich environments where the strong force could operate without electrical limitation. On Earth, the same principles apply on a smaller scale. Nuclear reactors rely on neutrons to sustain controlled fission reactions. A neutron enters a heavy nucleus, destabilizing it and causing it to split. This releases energy and more neutrons, which continue the process. The key is that neutrons can enter the nucleus easily because they are not repelled by electric charge. The strong force then takes over, redistributing energy and binding the resulting fragments. The entire process depends on neutron access to the nuclear interior. Even outside of energy production, neutrons are used as tools to study matter. Neutron scattering experiments allow scientists to probe the structure of materials at the atomic level. Because neutrons interact primarily through the strong force rather than electromagnetic force, they can reveal information that other probes cannot. Once again, the neutron's neutrality enables it to reach places where charged particles cannot go. At the deepest theoretical level, the neutron's role highlights an essential truth about nature. Forces do not act in isolation. The strong force is overwhelmingly powerful, but without the neutron, it could not build stable matter beyond the simplest forms. The neutron allows the strong force to express its binding power without interference. It is not merely held by the strong force. It enables the strong force to function effectively. There is also a paradox at the heart of this relationship. The strong force is short-ranged, and its effects diminish rapidly beyond the size of the nucleus. Electromagnetic repulsion, by contrast, has infinite range. As nuclei grow larger, the repulsion between protons becomes harder to overcome. Neutrons partially solve this problem by increasing binding without increasing repulsion, but only up to a point. Beyond certain sizes, no amount of neutron mediation can stabilize the nucleus. This is why the periodic table ends where it does. The neutron, powerful as it is, reveals the limits of stability as much as it creates it. This limitation leads to some of the most fascinating phenomena in physics. In extremely massive stars, when gravity overwhelms all other forces, protons and electrons combine to form neutrons. The result is a neutron star, an object held together by gravity and the strong force acting on neutrons packed to extraordinary density. In this environment, the strong force and neutron matter reach their extreme expression. The same principles that hold an atomic nucleus together are scaled up to astronomical proportions. The neutron's role in the strong force also reshaped human understanding of reality. Before its discovery, matter seemed governed primarily by electric charge. The neutron forced scientists to accept that the deepest structures of matter are governed by forces that do not announce themselves through everyday experience. The strong force does not produce light, magnetism, or static electricity. It operates silently, invisibly, but decisively. Neutrons are its perfect agents. In practical terms, every stable object you touch is a triumph of neutron, mediated strong, force binding. The solidity of a table, the durability of steel, and the resilience of bone all depend on atomic nuclei that remain intact over time. Chemical bonds may determine how atoms connect, but nuclear stability determines whether atoms can exist long enough to form those bonds. Neutrons ensure that this deeper level of structure remains secure. The phrase that neutrons hold atomic nuclei together through the strong nuclear force is therefore not a simplification but a doorway into understanding why the universe did not self-destruct. It explains how matter overcame internal conflict and achieved lasting form. The neutron does not overpower the proton, it complements it. It does not replace the strong force. It makes it workable. Through this quiet partnership, the universe gained the ability to build complexity, endure time, and give rise to everything from galaxies to life itself. This explanation is only part of the full story, but even in this first half, one truth becomes clear. The neutron is not just a participant in nuclear structure. It is the condition that allows the strongest force in nature to do its work without tearing matter apart. In that role, it stands as one of the most important contributors to the existence of stable reality. The idea that a free neutron is unstable, yet reveals deep truths about fundamental forces, seems at first like a technical detail of particle physics. In reality, it is one of the most illuminating clues we have about how the universe is constructed, and how stability itself emerges from interaction rather than permanence. The neutron's instability outside the nucleus is not a flaw or an exception. It is a window into the delicate balance of forces that govern matter at the most fundamental level. When a neutron is bound inside an atomic nucleus, it can remain stable for billions of years. But when it exists on its own, separated from protons and the nuclear environment, it decays in roughly 15 minutes. This transformation turns the neutron into a proton, an electron, and an almost massless particle called a neutrino. This process, known as beta decay, is not random destruction. It is a precise and lawful transformation governed by the weak nuclear force, another of nature's fundamental interactions. This simple fact already tells us something extraordinary. Stability is not an intrinsic property of a particle. It is not written into the neutron as an unchangeable feature. Instead, stability depends on context. Inside the nucleus, the neutron is stabilized by its interactions with other nucleons and by the strong nuclear force. Outside, when those interactions are absent, another force becomes dominant. The neutron's decay shows that matter is defined not only by what it is, but by where it is and what it interacts with. The weak nuclear force, responsible for neutron decay, is subtle and counterintuitive. It is far weaker than the strong force and electromagnetism, yet it has a unique role. It allows particles to change identity. Through the weak force, a neutron can become a proton. No other force permits this kind of transformation. This ability makes the weak force essential for the evolution of the universe, even though its effects are rarely noticed in everyday life. The instability of the free neutron reveals how these forces compete. Inside the nucleus, the strong force dominates, binding neutrons and protons tightly together. The weak force is still present, but its effects are suppressed by the energy environment of the nucleus. The neutron does not have enough freedom to decay without disrupting the entire nuclear structure. Outside the nucleus, the strong force no longer binds the neutron, and the weak force can act unhindered. The neutron then follows its natural tendency to decay into a more energetically favorable configuration. This decay is not arbitrary. It reflects the slight difference in mass between the neutron and the proton. The neutron is just a little heavier. This extra mass becomes energy during decay, producing the electron and neutrino. If the neutron were lighter than the proton, the opposite process would occur, and protons would decay into neutrons. Hydrogen, the simplest and most abundant element in the universe, would be unstable. The existence of long-lived hydrogen atoms depends directly on the neutron's instability rather than the proton's. In this way, the neutron's decay ensures the stability of ordinary matter. The early universe provides a dramatic demonstration of this principle. In the first minutes after the Big Bang, protons and neutrons existed in nearly equal numbers. As the universe cooled, free neutrons began to decay. Only those that quickly became bound in nuclei survived. This decay reduced the neutron population, setting the ratio of hydrogen to helium in the universe. If neutrons were stable on their own, the universe would contain far more helium and far less hydrogen. Stars would evolve differently, and life as we know it might never have emerged. The neutron's instability shaped the chemical composition of the cosmos. This process also reveals the delicate timing of cosmic events. Neutrons decay on a timescale of minutes, while nuclear fusion in the early universe occurred within that same window. The fact that these timescales align is not trivial. It suggests that the laws of physics are finely balanced to allow complexity. The neutron's short free lifetime and long-bound lifetime work together to create a universe that is neither too simple nor too chaotic. The decay of a neutron also exposes the strange nature of the weak force itself. Unlike other forces, the weak force violates certain symmetries that were once thought sacred. It distinguishes between left and right, between different orientations of particles. Neutron decay experiments played a key role in discovering that nature is not perfectly symmetric. This discovery reshaped modern physics and forced scientists to rethink assumptions about the fundamental laws of reality. The neutrino produced in neutron decay adds another layer of mystery. For decades, neutrinos were thought to be massless and nearly undetectable. Their existence was proposed precisely to account for missing energy in beta decay. Without neutrinos, neutron decay would violate energy conservation. The fact that such an elusive particle is required to make neutron decay work correctly reveals how deeply interconnected the universe is. Even the decay of a single particle involves entities that can pass through entire planets without interaction. The neutron's instability also plays a crucial role in nuclear physics on Earth. In nuclear reactors, free neutrons are produced in fission reactions. These neutrons must be carefully controlled. If they decay too quickly or are absorbed improperly, the chain reaction fails. The predictable lifetime of free neutrons allows engineers to design systems that harness nuclear energy safely. Once again, instability becomes a tool rather than a problem. In stars, neutron decay and transformation influence nuclear pathways. In certain stellar environments, neutrons are captured by nuclei before they decay, leading to the creation of heavier elements. In other situations, decay dominates, altering the balance of nuclear reactions. The competition between capture and decay determines which elements form and in what quantities. The neutron's instability is therefore a creative force in cosmic chemistry. On a conceptual level, the neutron teaches us that permanence is rare at the fundamental scale. Particles exist in states of potential change. What appears stable is often the result of suppressed processes rather than absolute immutability. The neutron decays not because it is weak, but because it is allowed to. Inside the nucleus, decay channels are blocked or energetically unfavorable. Outside, they open. This principle applies across physics, from excited atoms emitting light to unstable particles transforming into others. The neutron also bridges the worlds of matter and force. Its decay shows how forces can change particles, not just move them. This challenges the classical idea that forces simply push or pull. At the quantum level, forces define what particles can become. The weak force does not merely act on the neutron, it rewrites it. This is one of the deepest insights of modern physics, and the neutron is one of its clearest examples. There is also a philosophical lesson embedded in neutron instability. Stability arises from relationships, not isolation. A neutron is stable when it is part of a system. Alone, it cannot remain what it is. This mirrors patterns seen in larger systems, where structures endure because of interactions rather than independence. The neutron, in its quiet decay, reflects a universal truth about existence itself. The experimental study of neutron decay continues to refine our understanding of fundamental constants. Precise measurements of neutron lifetime test the consistency of the standard model of particle physics. Small discrepancies could point to new physics beyond current theories. In this way, the neutron remains an active participant in scientific discovery, decades after its basic properties were first understood. The free neutron's instability is therefore not a minor detail, but a central feature of the universe's design. It determines the balance of elements, reveals the nature of the weak force, exposes hidden symmetries and asymmetries, and demonstrates that stability is contextual rather than absolute. Through the neutron's decay, we learn that the universe is not built from unchanging blocks, but from dynamic entities whose identities emerge from interaction. In this first half of the explanation, one conclusion stands out clearly. The neutron, when free, does not simply disappear. It transforms according to precise laws, and in doing so, it reveals the invisible forces that shape reality. Its instability is not a weakness, but a message written into the fabric of the universe, telling us how matter, force, time, and balance are woven together. The idea that neutrons power nuclear energy, stars, and element formation may sound like a sweeping statement, but it is, in fact, a precise description of how the universe generates and transforms energy at its deepest level. From the controlled environment of a nuclear reactor to the violent birth of elements in exploding stars, neutrons are the quiet drivers behind processes that shape both human civilization and cosmic history. Their lack of electric charge, combined with their mass and interaction through the strong force, makes them uniquely suited to initiate, sustain, and regulate some of the most powerful energy transformations known to nature. On Earth, the most familiar expression of neutron power is nuclear energy. In nuclear fission, a heavy atomic nucleus such as uranium-235 absorbs a neutron. Because the neutron has no electric charge, it can enter the nucleus without being repelled. Once inside, it destabilizes the delicate balance of forces holding the nucleus together. The strong nuclear force, which normally binds the nucleus, is suddenly redistributed. The nucleus splits into smaller fragments, releasing a tremendous amount of energy along with additional neutrons. These newly released neutrons go on to strike other nuclei, creating a chain reaction. This process illustrates a key truth about neutrons. They do not supply the energy directly. Instead, they unlock energy already stored in the nucleus. That energy comes from the binding energy of the strong force, which holds nucleons together. When a nucleus splits, some of this binding energy is converted into kinetic energy and radiation. Neutrons act as the triggers that make this conversion possible. Without neutrons, nuclear fission would be practically impossible to sustain. The same principle applies to nuclear fusion, though in a different form. In fusion, light nuclei combine to form heavier ones, releasing energy in the process. This is how stars, including our Sun, produce light and heat. While protons are the primary participants in fusion reactions, neutrons play a crucial supporting role. In many fusion pathways, neutrons are produced or absorbed, allowing reactions to proceed more easily by reducing electric repulsion. In stellar cores, where temperatures and pressures are extreme, neutrons help stabilize newly formed nuclei and enable the strong force to bind them together. The Sun's energy output, which sustains life on Earth, depends indirectly on neutron involvement. In the proton chain reaction that powers the Sun, protons are converted into neutrons through weak force interactions. These newly formed neutrons become part of helium nuclei. This transformation releases energy in the form of light and neutrinos. Every sunrise is therefore connected to neutron-related processes occurring deep within the Sun's core. In larger stars, neutron involvement becomes even more dramatic. As stars exhaust their fuel, they begin to fuse heavier and heavier elements. Each stage of fusion depends on the balance between electromagnetic repulsion and the strong nuclear force. Neutrons allow this balance to shift in favor of fusion by adding mass without adding charge. This makes it possible for nuclei to grow heavier without becoming immediately unstable. Elements up to iron are formed in this way, each step guided by neutron participation. Beyond iron, fusion no longer releases energy. Instead, the creation of heavier elements requires environments rich in neutrons. This is where neutron-driven processes dominate element formation. During supernova explosions, vast numbers of neutrons are released in a very short time. Atomic nuclei capture these neutrons rapidly, forming heavier and heavier isotopes. Some of these isotopes are unstable and decay into new elements. This sequence of neutron capture and decay produces many of the heavy elements found in the universe. This neutron-rich process explains the cosmic origin of elements like gold, platinum, and uranium. These elements are not formed in ordinary stars, but in catastrophic events where neutron densities are extreme. When two neutron stars collide, the universe briefly becomes saturated with free neutrons. In these moments, matter is reshaped at a fundamental level. The heavy elements created in these events are later scattered into space, becoming part of future stars, planets, and eventually living organisms. The neutron thus becomes a bridge between destruction and creation. The role of neutrons in stars also extends to their final stages. When a massive star collapses, gravity forces protons and electrons to combine, forming neutrons. The result is a neutron star, an object composed almost entirely of neutrons packed at incredible density. In this environment, neutrons are not just participants in reactions. They are the dominant form of matter. The gravitational energy released during the formation of a neutron star is immense, and it is partly converted into neutrinos and radiation that influence the surrounding cosmos. Neutron stars themselves are powerful energy sources. Their rapid rotation and intense magnetic fields produce beams of radiation that sweep through space like cosmic lighthouses. These pulsars are among the most precise natural clocks known. Once again, the neutron proves capable of sustaining extreme forms of energy and structure. The same particle that gently stabilizes atomic nuclei can, under different conditions, support objects with masses greater than the Sun compressed into a city-sized sphere. Back on Earth, neutron-driven energy has shaped human history. Nuclear reactors provide electricity without emitting carbon dioxide, offering both promise and controversy. Nuclear weapons demonstrate the destructive potential of uncontrolled neutron-driven reactions. In both cases, the underlying physics is the same. Neutrons initiate and sustain reactions by accessing the nucleus directly. Their neutrality is the key that unlocks nuclear energy. Neutrons are also essential in the controlled synthesis of new elements in laboratories. By bombarding nuclei with neutrons, scientists can create isotopes that do not exist naturally on Earth. Some of these isotopes are used in medicine for diagnosis and treatment. Others help researchers understand nuclear structure and fundamental forces. The ability to harness neutrons in this way extends the periodic table and deepens our knowledge of matter. The energy associated with neutron processes is not limited to dramatic events. It also plays a role in the long-term evolution of planets. Radioactive decay, driven by neutron imbalance in certain nuclei, produces heat inside planetary interiors. This heat drives geological activity, including volcanism and plate tectonics. Earth's dynamic surface, which supports life, is partly sustained by neutron-related nuclear processes occurring deep underground. There is a profound unity in all of this. The same neutron that triggers fission in a reactor also participates in fusion in stars and element formation in cosmic explosions. The scale changes, but the principles remain the same. Neutrons enable the strong force to release energy in controlled or explosive ways. They allow matter to reorganize itself, releasing energy in the process. The power of the neutron lies not in aggression, but in access. Because it carries no electric charge, it can go where charged particles cannot. It enters nuclei, participates in binding, and reshapes matter from within. This ability makes it the universal catalyst of nuclear energy across the universe. In this first half of the explanation, one idea becomes increasingly clear. Neutrons are not merely byproducts of nuclear reactions. They are the agents that make those reactions possible. They power stars, light cities, forge elements, and drive the energetic evolution of the cosmos. Without neutrons, energy would remain locked inside nuclei, stars would never shine, and the rich diversity of elements that make up the world would never have come into existence. Understanding neutrons reshapes our view of matter, energy, and the universe, because the neutron sits at a crossroads where all three concepts meet. It is not merely a particle among many, but a lens through which the deeper structure of reality becomes visible. When scientists first encountered the neutron, they did not just add a new entry to a list of particles. They were forced to reconsider how matter holds together, how energy is stored and released, and how the universe evolves from its earliest moments to its most extreme states. Before the neutron was known, matter appeared deceptively simple. Atoms were thought to be made of negatively charged electrons orbiting positively charged nuclei. The nucleus itself was imagined as a cluster of protons, and electric charge seemed to be the organizing principle of everything. This picture was unstable both physically and conceptually. Protons alone could not form stable nuclei, and the observed masses of atoms did not match expectations. The discovery of the neutron shattered this incomplete view and replaced it with a richer, more subtle understanding. With the neutron in place, matter became a layered structure governed by multiple forces. Electric charge no longer dominated at every level. Instead, it became clear that different forces rule different scales. Electromagnetism governs chemistry and everyday interactions, while the strong nuclear force governs the heart of matter itself. The neutron, neutral and massive, revealed that stability at the deepest level does not come from attraction between opposites, but from balance within a tightly bound system. Matter, at its core, is not held together by visible forces, but by invisible ones operating over microscopic distances. This realization transformed our understanding of energy. Nuclear energy, once hidden inside atoms, became accessible and comprehensible. The neutron showed that enormous amounts of energy are stored in the binding of nuclei, far exceeding the energy of chemical reactions. This discovery did not just change physics, it altered history. It led to nuclear power, nuclear medicine, and nuclear weapons. Humanity gained the ability to tap into the same forces that power stars, all because the neutron provided access to the nucleus. At a deeper level, the neutron forced scientists to rethink what energy actually is. Energy was no longer just motion or heat. It was binding, structure, and potential. The mass of a nucleus is less than the sum of its parts because some mass is converted into binding energy. This missing mass is not gone. It is the energy that holds the nucleus together. The neutron, by participating in this binding without adding electrical complications, made this concept tangible. Matter and energy were revealed as two aspects of the same reality. The neutron also reshaped our understanding of time and change in the universe. Its instability outside the nucleus showed that particles are not eternal objects, but processes. A neutron can become something else. Identity at the fundamental level is flexible, governed by probabilities and interactions. This challenged classical ideas of permanence and replaced them with a dynamic view of existence. Matter became something that evolves, transforms, and adapts over time. In cosmology, the neutron became a key player in the story of the universe's birth. In the first moments after the Big Bang, the balance between neutrons and protons determined which elements could form. The neutron's decay rate influenced the abundance of hydrogen and helium, shaping the future of stars and galaxies. A small change in neutron behavior would have produced a radically different universe. This sensitivity highlighted how finely balanced the laws of physics are, and how deeply the neutron is woven into that balance. As scientists explored extreme environments, the neutron continued to redefine expectations. In neutron stars, matter reaches densities beyond anything found on Earth. Atoms are crushed, electrons merge with protons, and neutrons dominate. These objects challenge our understanding of physics, pushing theories to their limits. The neutron, once seen as a supporting character in atomic nuclei, becomes the main substance of entire stars. Matter, energy, and gravity intersect in ways that stretch imagination and theory alike. Studying neutrons also transformed experimental science. Because neutrons carry no electric charge, they can probe matter in unique ways. Neutron scattering reveals the arrangement of atoms in materials, the behavior of magnetic fields inside solids, and the structure of complex molecules. This has applications ranging from materials science to biology. The neutron became not only an object of study, but a tool for discovery. The neutron's role in medicine further reshaped how science interacts with human life. Neutron-based imaging and therapies allow doctors to diagnose and treat diseases in ways that would otherwise be impossible. Radioisotopes created through neutron capture are used in cancer treatment and medical diagnostics. The same particle that binds atomic nuclei becomes a means of healing. This duality forces a reevaluation of the relationship between fundamental physics and everyday human experience. On a philosophical level, the neutron undermines the idea that reality is built from simple, independent pieces. Its behavior shows that context matters. A neutron is stable in one environment and unstable in another. Its identity depends on interaction. This challenges reductionist thinking and suggests that relationships are as fundamental as components. Matter is not just a collection of particles, but a network of interactions held in delicate balance. The neutron also revealed the limits of human intuition. We do not experience the strong force or the weak force directly. We do not sense neutrons passing through our bodies or stabilizing our atoms. Yet these unseen processes determine in everything we experience. The neutron teaches humility, reminding us that the most important aspects of reality may be hidden from direct perception. As physics advanced, the neutron became central to testing and refining fundamental theories. Measurements of neutron decay, mass, and magnetic properties provide stringent tests of the standard model of particle physics. Any deviation from predictions could signal new physics beyond current understanding. In this way, the neutron continues to guide scientific progress long after its initial discovery. The neutron's influence also extends to questions about the future of the universe. The behavior of nuclear matter under extreme conditions affects how stars die, how black holes form, and how heavy elements are distributed across galaxies. Understanding neutrons is essential to understanding cosmic evolution. They are not passive remnants of past events, but active participants in the ongoing story of the cosmos. What emerges from all of this is a transformed world. Matter is no longer static or simple. Energy is not just something that flows, but something that binds. The universe is not a machine built from rigid parts, but a dynamic system shaped by subtle interactions. The neutron sits quietly at the center of this picture, neutral in charge but profound in consequence. In this first half of the explanation, the neutron emerges as a unifying concept. It connects the smallest scales of particle physics with the largest scales of cosmology. It links matter to energy, stability to change, and simplicity to complexity. By understanding the neutron, we do not just learn about one particle. We gain insight into how the universe holds itself together, transforms itself, and continues to evolve.